Okay, let's talk about the section 5.5. The real zeros of a polynomial function. Okay. So first we have the long division. Remember that division and factoring theorem. The long division is the following. If you have a polynomial fx over gx, it is equal to the another polynomial q of x plus r of x over g of x. Okay, this is long division where the degree of r of x is strictly less than the degree of g of x. Okay, and again, the numerator is called the dividend, and the denominator is called the divisor. And this q is called the quotient, and this r is called the remainder, r, only the r. Okay, so whenever you have a long division, you can always have those dividend, divisor, quotient, remainder, and you write them this way. This is called the division algorithm. Of a polynomial. Okay, division algorithm of polynomial. And if we multiply this equation by g of x, we multiply it by g of x, we will get fx is equal to the quotient times the divisor plus the remainder. Okay, so you multiply every term by g of x, you have this. And when this g of x is x minus c, for example, when g of x, this works for all the division algorithm. And especially when g of x is x minus c, then we will have this. Remember here, x minus c, the degree is 1. And we need the degree of the remainder strictly less than 1. It's strictly less than 1, strictly less than the degree of the denominator. So it implies the degree of the remainder in this case has to be 0. So r of x is a constant. Okay, r of x becomes a constant. When r of a constant, we can ignore x, just write r instead of r of x. And then this is an identity. It works for all x. Choose x equal to c. Choose x equal to c, then the left side becomes f of c, right side q of c and times c minus c plus r. C minus c is 0 times q of c is 0. So this implies r is equal to f of c. So this constant is the evaluation of the polynomial at the point c. Okay, so to summarize it, we have the so-called the remainder theorem. The remainder theorem says let f be a polynomial function if fx is divided by x minus c, it is divided by x minus c, then the remainder is R. The remainder is f of c. Okay? So that's exactly what we discussed here. Right? So when we go through this division logarithm, we choose a special divisor x minus c, then we notice that the degree of the remainder has to be 0. It's a constant, and then to determine the constant, we'll select the special point c, x equal to c, and the first term will disappear because c minus c is 0. So this is 0, so you will get r equal to fc. So this is called the remainder theorem. Okay. Let's see the example. Find the remainder if fx is equal to x cubed minus 4x squared and minus 5 is divided by a. What is a? A is x minus 3. Okay, x minus 3, c is equal to 3. You divide a polynomial by x minus c, then by remainder theorem, the remainder is f of 3. f of 3 is 3 cubed minus 4 times 3 squared minus 5. 3 cubed, 3 times 3, 9 times 3, 27. 3 squared is 9, 4 times 9, 36, and minus 5. It's negative 14, okay? It is equal to the negative 14. We can verify it. How do we verify it? Remember that there's the syntactic division. Let's try syntactic division, see if we get a negative 14 here. So x minus 3, so you put 3 here. You copy the coefficients. You have 1, negative 4. There's no x term, 0, negative 5. So you drop 1 here, 1 times 3 is 3. Negative 4 plus 3, negative 1. Negative 3 times 3 times negative 1 is negative 3. Addition is negative 3. And 3 times negative 3 is negative 9. Addition, negative 14. See, this is the remainder. Do you still remember the syntactic division? Remember that you drop the first term, and first it is only possible for the division by x minus c. You copy c here. You just copy the coefficients of a polynomial here, and if they're missing term, you put 0, and then you drop the first term down and use first term times 3, you get 3. You add a negative 4 with 3, you get negative 1. Negative 1 times 3, negative 3. You add 0 by negative 3, you get negative 3. Negative 3 times 3 here, negative 9. Negative 5 plus negative 9, negative 14. The same thing. The same stuff. But this one, you just do the evaluation. Here you have to still recall what the syntactic division is. Okay, so second, Second, the polynomial remainder theorem requires fx divided by x minus c. So here you have x plus 2. You write it like x minus -2. So c is -2. This is the tricky point. C is -2. Okay, then by the remainder theorem, the remainder is f of -2, or -2 cubed minus 4 times -2 squared minus 5. -2 cubed is -8. -2 squared is 4. 4 times 4, 16 minus 5. -29. Okay, this is -29. Let's try the syntactic division also. We have the same thing. 1, -4, 0, -5. We have the same polynomial. Of course, this row is the same. And c is changed. So we got 1. 1 times -2 is -2. It's a -6. -2 times -6 is 12. The addition is 12. 12 times -2 is -24. See? Same thing. Okay, so this is a good exercise. We first apply the remainder theorem, and second, we also recall the syntactic division. Okay. Don't forget the syntactic division. Sometimes it is a way to verify your answer. By the remainder theorem, we see that if fc is 0, if f of c is 0, this term is missing. If this term is missing, then you will have fx as a product of q of x times x minus c. Then x minus c becomes a factor. Okay? If this term is 0, x minus c is a factor. So that's a factor theorem. Okay? So the factor theorem, let f be a polynomial function, then x minus c is a factor of fx if and only if fc is 0. So this term has to be 0. Okay? So the idea just comes from this part. If it is a factor, there's no remainder. So fc is 0. If fc is 0, then it becomes a factor. Right? Okay. So now we have two theorems. One is called the factor theorem. This is the second theorem. The other one is called the remainder theorem. And of course, we also have that division algorithm. Let's try this. Factor theorem. So use the factor theorem to determine whether the function fx equal to 2x cubed minus x squared plus 2x minus 3 has a factor okay, part A, x minus 1. We want to determine if this polynomial function has a factor x minus 1. Then by the factor theorem, in order to determine it is a factor or not, we compute f of 1. We check the value of f of 1, f of c. So f of 1, 1 to whatever power is 1. So it's got 2 minus 1 plus 2 minus 3 is equal to 0. Very good. It is 0. 0 means x minus 1 is a factor of fx. That's it. That's the simplest thing. The second one is where is it? X plus 3. Yeah. X plus 3. Well, x plus 3. Let's try it. Did I make a mistake? No. By the x plus 3 should be written as x minus negative 3 so that you can easily determine c. So by factor theorem, we compute f of negative 3. So here that's an important thing. It's a negative 3. So you get 2 negative 3 cubed minus negative 3 squared plus 2 times negative 3 and minus 3. Just do substitution. So negative 3 cubed is negative 27. Negative 27 times 2, negative 45. Negative 3 squared is 9. 2 times negative 3, negative 6 minus 3. Negative, 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 negative. Even when I don't compute it, it's not equal to 0. It's a negative number for sure. And then, since this evaluation is not a 0, x plus 3 is not a factor. X plus 3 is not a factor. So you don't have to do the division and see the stuff. Okay, so the remainder theorem, factor theorem. The remainder theorem comes from the division algorithm, and then it gives us the factor theorem. Cool. And next, let's talk about the number of real zeros. It says a polynomial function cannot have more real zeros than its degree. So it means if you have a polynomial of degree 3, you cannot have 4 real zeros. Okay? So why is this? Remember that when we have x minus c as a factor, then you have a solution. And continue that, you will discuss q. Q possibly can be written as another polynomial times x minus c1 and times x minus c. This is x minus c. Q is written as q1 times x minus c1. And you continue this, we call it factorization. Eventually, you possibly have x minus c1, x minus c2, and together with the first one. and this product is going to be fx. Each of them has degree 1, so the sum is at most is at the most degree with another polynomial, which you cannot find the solutions, and this degree should be less than the degree x minus c1 x minus c. This degree should be less than or equal to the degree of fx. And here you have possibly k, not k, let's not use k. You have L solutions or L zeros. Then this L should be less than the degree of f. Okay, so it means whenever you have a solution, it will be the number of the total solutions should be less than the degrees. You have a solution, you have a factor. Okay. This is exactly the factor theorem. C is a solution, x minus c is a factor. It's a factor theorem. Right? Okay, so here we do not possibly know exactly the number of the real zeros so far, but we do know that you cannot have more real zeros than the degree. So we have an upper bound. So remember that when we have a quadratic polynomial, sometimes it does not have a real zeros. Sometimes it has 1, but it's a repeated one. Sometimes it has 2 different real zeros. But either way, it can you will not see it has 3 real zeros. That's impossible, right? Okay. This theorem, it does not give us an algorithm. It's not like the factorization theorem, the remainder theorem or the factor theorem. The remainder theorem, factor theorem both contain some computation, but the number of real zero theorem does not contain any formula. It's just an idea, okay, a common sense. Now let's talk about so-called the rational zeros theorem. Okay, what is a rational zeros theorem? Let's first state that and we check. Let f be a polynomial function of degree 1 or higher of the form higher of the form fx is equal to a sub n x to n, a sub n minus 1 x to n minus 1, a sub 1 x and plus a 0. Okay, so we have a polynomial function, and the requirement is that where a0, a1, an are integers. So we only study integer coefficients polynomial for this part, rational zero theorem. We only allow integer. And if, I don't know the zeros, but if P over Q in lowest terms, which means you cannot cancel, there's no common factor. If P over Q is a rational zeros of f, then P must P divides A0 and Q divides AN. Okay, so if you have some rational solutions, then this rational solution has to satisfy some condition. This is the condition. Condition means the numerator divides a constant term, denominator divides the leading coefficient. The middle coefficients are not important, but those two end coefficients matter or controls the rational solutions. Okay, so we are not going to prove it, but you have to memorize it. Rational zero solutions. For integer coefficient polynomials, if you have a rational function, a rational solution, my bad. If you have a rational solution, numerator divides a constant term, denominator divides a leading term, leading coefficient. Okay? How do you memorize it? I give you a way to memorize it. So you just pick up the simplest one. 2x plus 3 equal to 0. Let's put the negative 3 here. Doesn't matter. Be careful. A1, AN, A0. All the stuffs contains a coefficient. They can be positive and negative integers. It's not always positive integer. So for this example, A1, the AN is A1 is 2. A0 is negative 3. But the solution, you know that the solution is 3 halves. The solution is 3 halves, so P over Q. P is 3, Q is 2. So Q divides the leading term. P divides the constant term. Leading coefficient. Q divides the leading coefficient. Q divides the leading coefficient. P divides a constant term. Then this is a way to memorize it. Otherwise, you may be confused. Okay, so what is the usage of it? The usage is the following: least potential rational zeros. Fx is equal to 2x cubed plus 11x squared minus 7x and minus 6. Okay, then let's check P. The numerator divides this the constant term. So it divides the constant term. P actually can be the factor of negative 6. So P can be plus minus 1, plus minus 2, plus minus 3, and plus minus 6. They are all the coefficients of they are all the factors of a negative 6. And the Q has to be the factor of 2. So Q can be plus minus 1 and plus minus 2. Okay, then once you've got all possible values for P and Q, P over Q can be, well, let's check. 1 over 1 plus minus 1, 2 over 1 plus minus 2, 3 over 1 plus minus 3, 6 over 1 plus minus 6, always plus minus. And then 1 over 2 plus minus 1 half. 2 over 2 is 1. 1 is repeated, so you don't copy it. 3 over 2 is a plus minus 3 halves. 6 over 2 plus minus 3 is repeated. So this is a potential list of the rational zeros. If the function has a rational zero, it has to be one of them. So you see, we narrow down the range of our rational zeros to this selection. So that's a application of a rational zero theorem. The rational zero theorem can be only applied to the integer coefficient polynomials. If you have non-integer, it doesn't matter which position, not only the leading and the constant term. for any other place, if you have a non-rational, irrational numbers, sorry, for any other place, if you have a non-integers, other numbers, then you can never apply this rational zero theorem. All the coefficients must be integers, then you can do that. And by the rational zero theorem, we have this, the list of the potential rational zeros. Okay, so that's a rational zero theorem. And now, when you have the candidates, what you can do, just try, test all possible stuff. Okay, so find the real zeros of a polynomial function. This is one of important topic in applications. We want to solve the equation of polynomials. Okay, so example. Find the real zeros of the polynomial function fx equal to 2x cubed plus 11x squared minus 7x and minus 6, the same polynomial function. First of all, fx has degree 3, so it has at most 3 real zeros. So this type of problem, find all solutions, find this, find that, it is always a comprehensive, difficult problem. You have to use all the knowledges you have learned and figure it out. There's no standard process to find the solutions. Here, we just study the special polynomial function, apply the special technique, okay? So first, we notice that if you find 3 solutions, it's done, okay? So it can have at most 3 real zeros. And this is an integer coefficients polynomials. If you have rational zeros, the rational zeros should be in this list. So the list of potential rational zeros is obtained above. Why we start with the rational zeros? Because we have this rational zero theorem. If you have other powerful theorem, you will start with other topic, with other direction. But here, since we only have the rational zero theorem, we just start from this. Okay, let's check here. Let's copy it. They are just potential rational zeros. We don't know if it is or not. How do we know it is a rational zero? It is a zero or not? Just try, evaluate. You are going to evaluate the function at 1. You evaluate the function at -1 and figure out the values. Of course, we always start from the simple test, right? We will not start from 3 halves first, because 3 halves you need to compute the cube, the 3 halves cube. That's more complex. So I don't know. I will start from f1 first. f1, let's check. It's 2 plus 11 minus 7 minus 6. Okay, 0. Okay, we're lucky. So f1 is 0. It means 1 is a real 0. 1 is a real 0. So we start from 1, we're lucky. It's not the common case, but for this example, it's a good. Once we get a 1, we are going to do the division and reduce f from degree 3 to degree 2. Because it is 1, then x minus 1 is, 1 is a 0, then x minus 1 is a factor. X minus 1 is a factor. Okay, when you have a factor, then I want to do the division. How do we do the division? Let's try the syntactic division. So syntactic 2, 11, negative 6, 7, negative 6. And 1 is here. You got the 2, 13, 6, 0. Okay, see? And this implies fx is equal to x minus 1 times here, constant linear square term, 2x squared plus 13x and plus 6. See? Okay, once you reach a quadratic polynomial, every time, for whatever example, if you are supposed to find all the real solutions, when you reach quadratic polynomial, you will not apply any complex theorem. You will always apply the trick you learned in the quadratic polynomial or even the root formulas. For this one, we can factor it like this. 2 is factored as 2 times 1. 6 is 1 times 6. 2 times 6 is 12. 1 times 1 is 1. The addition is 13. See? So this is exactly x minus 1. 2x plus 1. X plus 6. Okay. And then they give us x equal to 1 or x equal to negative 6 or x equal to negative 1/2. 2x plus 1 equal to 0. X is negative 1/2. So we do have 3 rational solutions. And you can see that they are all in this list. So negative 6 is here, negative 1/2 is here. Right? So that's our first example. In our first example, we reduce the problem from degree 3 to degree 2 by this factor theorem. When you have degree 2 polynomial, quadratic polynomial, you can either use factorization, cross-factorization process, or you use a root formula to find the solutions. Sometimes there's no solution. If there's no solution, for example, if this part there's no solution, you will say the unique solution is x equal to 1. Okay? Then then the original polynomial of degree 3 will just have 1 root. Okay? So the list is the solution set. Very good. Okay. Let's see more example. This problem, there's no easy way to, and there's no faster way. All the ways are more or less the same. It is sometimes tedious. So find the real zeros of fx equal to x to 5 minus 5x to 4 plus 12x cubed minus 24x squared plus 32x and minus 16. Okay, well, it's very long. It's a degree 5. Degree 5 have 6 terms. And write f in factored form. In factored form. Okay, so f has at most 5 real zeros. F can have at most 5 real zeros. Let's try to list the potential real zeros. So P can be plus minus 1, plus minus 2, plus minus 4, plus minus 8, plus minus 16. Q can be plus minus 1. Okay. Well, then P over Q can be 1 over 1, 2 over 1, 3 over 1, 8 over 1, and 16 over 1. So you get plus minus 1, plus minus 2, plus minus 4, plus minus 8, plus minus 16. This list is a list of all potential rational zeros because you have an integer coefficient polynomial. Okay, and let's start. We will always start from 1. We'll start from the simple stuff. Let's try f of 1. 1 minus 5 plus 12 minus 24 plus 32 minus 16. What do we have? 1 plus 12 is 13 plus 32. Minus 5 minus 29 minus 16. It's 45 minus, oh good, 45 equal to 0. So 1 is the solution. 1 is a solution. 1 is the solution. We are going to do the long division to find the quotient. Okay. So we have 1, negative 5, 12, negative 24, 32, negative 16. 1. So we drop 1 down. 1, negative 4, negative 4, 8, 8, negative 16, negative 16, 16, 16, 0. Excellent. I always do the product here, and product here, and product here, and product here, and product here. The syntactic division. So fx is x minus 1. This is a divisor times a quotient. 0, 1, 2, 3, 4. Okay, so it's x to 4 minus 4x cubed plus 8x squared minus 16x plus 16. Okay, so we have this factorization at least. Well, what's next? Next, you are going to continue the study for this polynomial. For this polynomial, you are going to go through this again. So for x to 4, 4x cubed plus 8x squared minus 16x and plus 16. If it has a rational solutions, so P can be plus minus 1, plus minus 2, plus minus 4, plus minus 8, plus minus 16. This time you are talking about this 16. And the Q can be plus minus 1 here, the leading coefficient. Then P over Q can be, which is plus minus 1, plus minus 2, plus minus 4, plus minus 8, and plus minus 16. Again, you're going to start from 1. 1 is the simplest number. So you get this function. It's a 1 to 4 minus, it's just 1, minus 4 plus 8 minus 16 plus 16. Unfortunately, this moment is negative 3, 5. It's equal to 5. It's not equal to 0. So 1 is not the solution. 1 is not the solution of this part. It's not. 1 is the solution for the whole thing, but not for this part. 1 is examined. Let's try negative 1. So you got a negative 1 to 4 minus 4 times negative 1 cubed plus 8 negative 1 squared minus 16 negative 1 plus 16. So it's a 1 plus 4. It's negative 1 cubed is negative 1 times a negative 4 is a positive 4 plus 8 plus 32 plus 32. It's not 0. Positive, 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 positive. So negative 1 is not a solution. You see, for this example, we have bad luck. We already tested two numbers. They are not solutions. And let's continue. Let's continue. We have 2. Then we got 2 to 4 minus 4 times 2 cubed plus 8 times 2 squared minus 16 times 2 and plus 16. What is 2 to 4? 2 to 4, 2 square square, 2 squares 4, 4 squared 16, minus 2 cubed is 8 times 4, 32, plus 32, minus 32, plus 16. 32, 32 cancel, 16 plus 16, 32, minus 32, 0. Okay, fortunately, 2 is a solution. 2 is a solution. Let's do the syntactic division for this polynomial. X minus 2 is a factor. So you put 1 here, 2, negative 2, negative 4, 4, 8, negative 8, negative 16, 0. Okay, so this implies x to 4 minus 4x cubed plus 8x squared minus 16x plus 16 is equal to x minus 2. This is a factor, and times a polynomial determined by this, x cubed minus 2x squared plus 4x minus 8. Wow, this polynomial is factored as this, so the original f becomes x minus 1 times x minus 2 times this term. Okay? You have to repeat this process again. You have to repeat it. You will find the potential list of the rational solutions will be something, and then you try it again and again and again. In this place, if you study this polynomial a little bit, x cubed minus 2x squared plus 4x minus 8, we group them, the first two terms together and last two terms together. And for the first two terms, you factor out x squared. For last two terms, you factor out 4. See, it's a tricky process. And then x minus 2, x minus 2, they are the common factor. So you factor out x minus 2, you will get x squared plus 4. Okay, so the original polynomial fx can be written as x minus 1, x minus 2. You have a x minus 2 here, x minus 2 here, square. And then plus x squared plus 4. And this polynomial, if you check the discriminant, is negative, so this polynomial has no real zeros. X squared plus 4 can never be 0. So this implies f has real zeros 1, 2. 2 is repeated. Okay, so that's a real zeros, 1 and 2. And also f is factored as x minus 1 times x minus 2 squared and times x squared plus 4. Here. 2 if you want to make it precise with multiplicity 2. 1 has multiplicity 1, but this number 2 has multiplicity 2. Okay? Let's stop this video and we continue the discussion in the next video. in the current video, what we have learned. In the current video, what we have learned. So the first is long division. So basically just do the division. We have the division algorithm of a polynomial. And from this division algorithm of polynomial, we have this remainder theorem. Remainder theorem says the remainder, if you divide by x minus c, just a special case, if you divide a polynomial by x minus c, the remainder is fc. Okay? In the remainder theorem, you will get the factor theorem. X minus c is a factor if and only if there's no remainder. Fc is equal to 0. Okay? And after that, we learn the number of real zeros. A polynomial can have at most n real zeros if its degree is n. At most n. No more real zeros than the degree. So this is a number of real zeros. It's a guideline. It just says we cannot have a lot, but it does not say how many we have. It's a guideline. It's a very rough guideline. And next, we learn the rational zero theorem. The rational zero theorem can only be applied to the integer coefficient polynomials. If your coefficient is the square root of 2, then forget about the rational zero theorem. Okay? The rational zero theorem says if you have a rational zero, the numerator divides a constant term, denominator divides a leading coefficient. Let's give us the necessary condition. And then with the rational zero theorem, we can list the potential rational zeros. When you have the list of the potential rational zeros, you just have your job, try them. Okay? When you have this potential list, there's no other possible way for the rational zeros. You just try them. If some of them satisfy the condition, they are the real zeros. If they are not satisfy the condition, it just means this polynomial has no rational zeros, but it doesn't mean the polynomial has no real zeros. Okay? So for example, let me here there's examples, long, very long. The first example is simple, but second example is extremely long. You just go back and check it. Let me make one example. For example, let's say x squared plus 3x plus 1 fx. Fx is x squared plus 3x plus 1. It's a integer coefficient polynomial. Then the p can only be p the factor of 1, so plus minus 1. Q can be plus minus 1. The factor of the leading coefficient. So p over q can be plus minus 1. You just try it. F1 is 1 plus 3 plus 1 is 5. Not equal to 0. F negative 1 is 1 minus 3 plus 1 is negative 1, not equal to 0. So 1 and negative 1 are both non-zero, are both not 0. So what we can say? We can only say fx has no rational zeros. It has no rational zeros. In fact, it's a quadratic polynomial. What are the solutions? X is equal to, denominator is 2a, numerator is negative b plus or minus square root of a b squared minus 4ac. So you have two solutions, negative 3 plus root 5 over 2 or negative 3 minus root 5 over 2. They are both irrational. So this polynomial has solutions, real solutions, but it does not have rational solutions. Okay? So that's an example. Not every polynomial, every integer polynomial has real solutions. That's not the case. Sometimes, even for this simple one, it does not have a rational solutions. Okay? Okay, so we only discuss the special case and try to apply the property. Okay, we stop this video and continue in the next video about this section. This section is a long section. Okay, do your exercise. Thank you.